This video chapter focuses on the various minerals that constitute carbonate sediments, and we'll see that the mineralogical variation is quite simple, dominated by 4 or 5 carbonate minerals, of which only 2 dominate in ancient carbonate sediments. Throughout the course, we'll see that the life forms that contribute to the formation of carbonate sediments is quite complex and interactive, but the resulting mineralogies, that are the residues of life's carbonate metabolic activities, are relatively simple. And in ancient rocks, there are only 2. When we think of carbonate sediments, this is the typical scenario we visualize, with a variety of corals and coralline algae binding those corals together, forming what are, in a reef, a wave-resistive structure. The dominant minerals here in modern oceanic reefs are aragonite and magnesium-calcite. So what makes up the world's carbonate sediments, modern and ancient? Well, carbonate sediments can accumulate whenever we have chemistries where the waters are supersaturated with respect to calcium carbonate, and there's not too much siliciclastic input to dilute the carbonate accumulation. Carbonate sediments are defined as sediments which contain more than 50% carbonate minerals. Across the world, although they form largely from the activities of a carbonate secreting biota, carbonate sediments can also accumulate in lakes, rivers, around springs, in soils, and as cave deposits, speleothems. Carbonate minerals are reactive, and so once they're formed, they're extensively modified, both soon after formation and then in burial and uplift, by various processes of recrystallization, replacement, dissolution, and cementation. And they're interactive, so we can alternate between one set of processes and another. The main driving force for this is the movement of all carbonate sediments through the burial and uplift realms, through the eogenetic, the mesogenetic, and the telogenetic realms. Modern carbonate sediments are made up of 2 main minerals, aragonite and magnesium-calcite, tied back to the current magnesium-to-calcium levels in the world's oceans. Most carbonate sediments that are forming today retain evidence of the marine biota and their metabolic activities, which is driving the biomineralisation, which creates those carbonate sediments. If we go back into the ancient, 2 minerals dominate ancient carbonate sediments, and they are calcite, typically low-magnesium calcite, or dolomite. So together, calcite and dolomite make up more than 90% of all naturally occurring sedimentary carbonates. But alteration during burial and uplift dominates carbonate sediment history. Ancient carbonate sediments and hydrocarbon reservoirs will show varying levels of porosity related to the different styles of diagenesis to which that rock's been exposed. Typically, when we look at an ancient carbonate in the subsurface, almost all depositional porosity is gone. In some circumstances, we've created new types of secondary or diagenetic porosity. If we look at the suite of minerals that we see in all carbonates, we see 6 calcitic polymorphs, which we'll look at in detail in a moment, and also a calcium to magnesium metastability series related to the formation of different styles of sedimentary dolomite. This is a topic unto itself, and we devote a whole course to the study of sedimentary dolomite and the porosity and permeability evolution in ancient sedimentary dolomites. Coming back to those 6 calcitic polymorphs, if we look at biomineralisation and the carbonate minerals associated with biomineralisation across the world's biota, ranging from the bacteria, the Monera, dinoflagellates, they're dominated by calcitic, or in the case of the bacteria, depending on the metabolic chemistry in the areas in which they're forming, we can also see quite high levels of aragonite, and occasionally we see monohydrocalcite. If we look at the protists, we can see that the haptophytes, which include the coccoliths, are dominated by calcite. The phryophyta, the brown alga, are dominated by aragonite mineralogies. The red alga, the rhodophyta, we see a range of aragonite, calcite, and even a little bit of vaterite. The green alga are dominated by aragonite. The siphonophora are dominated by varying combinations of calcite or aragonite. Charophytes are dominated by calcite. Forams, mostly calcite, but also some aragonitic forms. Once again, these are tending to reflect the oceanic chemistry in which those systems are forming. And when we look at the fungi, they're dominated by calcite, as are the bryophytes. Vascular plants, the tracheophyte, we see a whole range of mineralogies ranging from calcite to aragonite and vaterite. Coming across to the animal kingdom, the sponges, we see varying combinations of calcite and aragonite. Corals, modern day corals, we see aragonite. Ancient corals, Paleozoic corals, we see calcite dominant. The platyhelminthe, calcite. The bryozoans, calcite or aragonite. Brachiopods, calcite. Annelids, calcite, aragonite, a little bit of vaterite. Mollusks, we see calcite, aragonite, vaterite, and sometimes early forms of calcite are preserved in some of the molluscan structures as monohydrocalcite. Arthropods, calcite, aragonite, vaterite. The sipunculids, calcite and aragonite. The echinoids, calcite. And in the teeth of some echinoids, we see sufficiently high magnesium carbonate levels to get an early protodolomitic association. So we can actually see dolomite forming in the teeth structures. And in the chordates, animals with a backbone, we see various calcite, aragonite, vaterite, monohydrocalcite, and also some amorphous carbonates. Life forms include the whole range of polymorphs of calcite, but calcite and aragonite are the dominant mineralogies. If we come on and look at the 6 polymorphs of calcium carbonate, those 6 polymorphs are calcite, aragonite, vaterite, calcium carbonate monohydrate, or ichthyoate as the hexahydrate form, and amorphous calcium carbonate. That list is in decreasing stability, with calcite being the most stable of the various polymorphs. This is true for both biomineralized and inorganic precipitates of calcium carbonate. The 3 anhydrous polymorphs are calcite, which has a hexagonal crystal structure, aragonite with a orthorhombic crystal structure, and vaterite, the least stable, with a hexagonal crystal structure. Then there are the hydrous forms of calcium carbonate. These are the monoclinically structured ichthyoate, cold temperature mineral, which is calcium carbonate 6H2O, and also calcium carbate monohydrate, or monohydritic calcite, calcium carbonate H2O, and also amorphous calcium carbonate, AAC, which has a variably hydrated form of calcium carbonate. These 3 hydrous forms are widely recognized metastable precursors to the crystalline species of either calcite or aragonite, the 2 more stable forms, with the calcite being the more stable form. Here's the calcitic form, clear sparry calcite as a butterfly twin. Here is acicular aragonite. Here is monohydrocalcite. And then here, forming in the Ica Fjord in southwest Greenland, we have this rather interesting hexahydrate form of calcium carbonate, ichthyoate, as a cold mineral precipitate, forming rather delicate structures in subaqueous waters, mapped there in that upper diagram, on the floor of this fjord, where we have cold water springs escaping, and we form this low temperature mineral, ichthyoate. It's only stable up to temperatures of around 6 degrees, but it's forming more than 1,000 submarine mineral columns that are growing up from the bottom of the fjord. As you can see, it's very quiescent water. These are quite delicate columns that are forming. We also see ichthyoate forming in other cold water environments. Here it's growing intrasedimentally as lenticular forms in Point Barrow in Alaska. As things warm up, it converts to calcite, typically after glendenite, or it will deliquesce and disappear. This is a concern for the ichthyoate columns, which are rather unusual and impressive natural phenomena. If we see warming of these cold water carbonates due to global warming, we may see collapse of these delicate structures. Then we have the monohydrate form, monohydrocalcite. This tends to be a rather ephemeral form of calcium carbonate. It does form around the margins of Lake Felmungaree in the southeast of Australia, where we see these cabbage-like structures, it's sometimes called cabbage tufa, associated with microbial activity. And of course, that matures into calcite. We see similar structures on the floor of Lake Kivu in eastern Africa. Then we have that variably hydrated form, the amorphous calcium carbonate form, forming as a precursor to many carbonate precipitative phases around the world. Okay, let's do a little bit of Chemistry 101. Coming back and looking at the calcium carbonate solubility equation, it's reversible. It means that calcite can easily dissolve or precipitate depending on the ambient chemistry, temperature, pressure conditions. So that main solubility equation, calcium carbonate plus water plus carbon dioxide, giving us free calcium ions plus bicarbonate ions, is reversible. And it's actually the summation of 4 equilibrium equations that are tied to the input and extraction of calcium carbonate. So we have a hydration reaction, CO2 plus H2O giving us bicarbonate, giving us carbonic acid. That's a slow reaction, but it's followed almost instantaneously by the breakdown of that H2CO through into H plus and bicarbonate. Now, if there's carbonate present in the solution, then that released proton, the H+, will react quite quickly with that carbonate to release more bicarbonate. At the interface between the water and the solid calcium carbonate, the equilibrium related to those products is calcium carbonate, giving us calcium and carbonate as a reversible reaction. So that overall reaction will move to the right when both carbon dioxide and calcium carbonate are dissolved into the solution. We see dissolution. Whereas it moves to the left, we precipitate calcite when carbon dioxide is removed from the solution and the calcium carbonate precipitates. So dissolution is favoured by falling temperatures or increasing pressures. Precipitation is favoured by rising temperatures and decreasing hydrostatic pressures. So what does that general simple chemistry mean in terms of the real world? Well, it tells us that we will see, as we have any environment on the world's surface where temperature or salinity is increasing and we're around calcium carbonate saturation, if we see CO2 bubbling off, then following Boyle's law, we'll see precipitation occurring. That type of scenario happens, either temperature or salinity increases, where the CO2 is being lost in situations where we have solar heating facilitating precipitation. In other words, we're seeing a form of retrograde solubility, where solubility increases as the temperature increases. It also means that cooling will mean that the water can hold more CO2 and dissolution will occur. If we have a scenario where we are increasing the pressure, then the water can contain more CO2 and thus it will promote dissolution. Whereas if we decrease the pressure, just imagine this is what happens when we have fault release, mimicking it here with the release of CO2 from a carbonated drink where that CO2 is coming out of solution. If we see any scenario in the subsurface where we get the escape of CO2, such as pressure release on a fault, then we will have a rapid precipitation of calcium carbonate. That same degassing reaction is also why we form on the world's surface various types of tufa and cave structures or cave precipitates, speleothems. They're all related to the escape of CO2, driving that precipitation reaction to the left as we release or degas the CO2. That's a very fundamental but very important equation when we come to think about what environments do we see this precipitation of calcium carbonate or the dissolution of calcium carbonate in the real world. Okay, let's step back now and look a little bit broader at the different styles of minerals that we see across the sedimentary realm. And there's only a few components in modern and ancient sedimentary carbonates. We can visualize them in this triangular plot by looking at calcium, magnesium, and iron carbonates. Sedimentary carbonate minerals are composed of carbonate combined with varying amounts of calcium, magnesium, and lesser amounts of iron. Ancient carbonates are mostly composed of calcite, that uppermost apex on the triangle, or dolomite, that midway between magnesium and calcium. Pure stoichiometric dolomite has the formula CaMgCO3 twice with a 1-to-1 distribution of magnesium to calcium. But in the real world, there's a variation around that pure stoichiometric dolomite. We can have more magnesium-rich dolomites and more calcium-rich dolomites. These two forms of early precipitative dolomite, calcium dolomite and magnesium dolomite, are early protodolomitic precipitates, and we deal with the chemistry and how these dolomites form in a lot of detail in the dolomites course. For now, in terms of mineralogy, let's just note that it's not pure 1-to-1 magnesium to calcium that we see in most sedimentary dolomites. We see a range of magnesium to calcium centered around that 1-to-1 ratio. Then we have pure magnesium carbonate, magnesite, and we have, if we include iron in the situation, pure iron carbonate, or we can have a range of iron to calcium to magnesium carbonates, such as Ferroan dolomite, ferrodolomite, or even anchorite in that 1-to-1 ratio, iron to calcium to magnesium. Typically, the iron carbonate minerals, those minerals with iron combined with varying forms of magnesium and calcium and carbonate, are more common as cements in sandstones, where the iron's coming out of the adjacent clays and precipitating Ferroan cements. We also see iron quite common in saline and hydrothermal precipitates. We also see in that combination between iron and magnesium minerals such as brunerite associated with magnesite, as we see in the Precambrian Mount Isa halokinetic terrain in northeastern Australia. Here we can see CO2 being removed from the bottom, and we are supplying oxygen during photosynthesis. That reaction where we're removing CO2 and supplying oxygen via photosynthesis, and this happens if we have cyanobacteria-covered floors, seagrass-covered floors, green algal-coloured floors, will induce or facilitate aragonite or calcite precipitation. Likewise, if we have waters percolating through a soil and absorbing CO2, so once again we're removing CO2 due to the activity of the soil biota, the microbes in the soil, then that water will become more acidic and it will dissolve some of the carbonate in that soil. Removing or adding CO2 in the natural environment controls whether we will precipitate or dissolve calcite in the sedimentary realm. If we move to the marine realm and now think about it in terms of temperature and solubility with increasing oceanic water depth, so on the vertical axis here we have water depth in kilometres, on the horizontal axis in the left-hand figure we have temperature, and on the right we have the percentage of carbonate in the sea bottom sediment versus depth. We can see that an increasing the ocean depth means we are decreasing the temperature and we're increasing the pressure. So that means more and more carbonate, which is stable in the near surface waters, will dissolve and will be held in solution as that calcium carbonate sediment, quite often coming from pelagic planktonic forms, is dissolving as it sinks to the deep ocean bottom. And we have a number of terms here that we use to describe that dissolution process. The lysocline is defined as the depth at which carbonate starts to dissolve, and the compensation depth is the depth where the water is so cold and the hydrostatic pressure is so high that all of the carbonate that was present as solids in the water column has gone into solution. It's disappeared. With that in mind, we can think about dissolution of the two main marine minerals that we see in the world's oceans today, aragonite and calcite. They have differing solubilities. There's an aragonite lysocline that's much shallower. Remember, the lysocline is the depth where we start to see the dissolution of that mineral phase. The aragonite lysocline is much shallower than the calcite lysocline. Likewise, the aragonite compensation depth is much shallower than the calcite compensation depth. So together, if we look at the depths of the aragonite lysocline and the calcite lysocline, along with their associated compensation depths, we effectively partition the modern ocean into 4 distinct zones based on their depth. There's a zone of precipitation where both aragonite and calcite are soluble. Below that, zone 2 is a zone of dissolution and precipitation where we have aragonite dissolving and we have calcite maintaining its saturation state. Then, as we go deeper, we move into zone 3, which is a zone of active dissolution. All the aragonite's gone and now the calcite's going. Below that, zone 4, we have a zone where no carbonate will accumulate. That's known as the calcite compensation depth. Sometimes it's generalized as the term carbonate compensation depth, but to be exact, we should think of it in terms of an aragonite compensation depth, which in all the world's oceans is a much shallower depth than the calcite compensation depth. Currently, those depths are not the same in the world's main oceans. Currently, the calcite compensation depth is at a depth of around 5,500 meters in the Atlantic Ocean, while it's much shallower at around 3,500 meters in the Pacific Ocean, related to the differing chemistries of those oceans. Then there's the scenario where if we bring those deep ocean waters back up to the surface by upwelling, then we'll see those now cold waters containing high levels of calcium carbonate in solution being brought to the surface. The pressure will decrease, the temperature will increase. So we will see that water, as it upwells into shallower environments, precipitating the carbonate minerals. And in a fairly recent paper by Moneka and others in 2023, they used upwelling to explain the widespread saturation for carbonate muds on the Bahamian platform. Still contentious. Others argue that there's a lot more biomineralisation effects for the mass precipitation of carbonate muds on the Bahamian platform. And we'll get into that a little later in the course. If we think about the various iron carbonates, these are typically found not so much in the marine carbonates, but as cements in siliciclastic sediments, where they tend to form as orthogenic cements in the pores of various siliciclastic host rocks. We'll also see them where we have hydrothermal fluid crossflows moving into the environment of interest. Much of the iron's being sourced in nearby mafics or in dewatering clays. Siderite tends to occur along with anchorite in a variety of metamorphosed ironstones and sedimentary banded iron formations, as well as in carbonatites. Anchorite being one of the minerals of the dolomite siderite series, which we looked at in a bit more detail in our economic geology courses, where it's a common gangue mineral in association with Faroe and dolomite in various types of base metal precipitates. Here we can see in the Jurassic Tilge Formation on the North Sea in the Norwegian sector, clear lenticular siderite post-dating the quartz overgrowths. I'm not going to worry too much more about iron carbonates in this carbonate course. We do deal with them in a bit more detail in the various base metal courses that are also offered online. Okay, let's come back and look at the main sedimentary minerals. These are the four main minerals we see in the marine realm: calcite, magnesium calcite, sometimes called high magnesium calcite, aragonite, and dolomite. They have differing crystallographic systems. They have differing levels of magnesium carbonate. Low magnesium calcite typically is defined as that which contains less than 4 mol% of magnesium carbonate. High magnesium calcite contains between 4 and 30% magnesium. Aragonite, once again, very low levels of magnesium. And dolomite in that range, as we discussed before, in sedimentary dolomites, between 40 and 55 mol% magnesium carbonate. In terms of their stability, calcite is by far the most stable of the calcium carbonate forms. Magnesium calcite and aragonite are metastable forms, and they will alter to calcite. Dolomite is a stable mineral in the sense that it maintains a mineralogy that is roughly 1:1 calcium to magnesium, but it evolves increasingly towards that stoichiometric 1:1 ratio with burial and fluid crossflows. We devote a whole course to dolomite and its mineralogy and its evolution in the subsurface. Let's have a look at some forms of calcite. So here's a bit of carboniferous calcite spar. Here is some blades of high magnesium calcite in a marine cement. Here is some acicular aragonite as a marine cement. And here is some saddle dolomite from the Dolomite region in Russia as a diagenetic hydrothermal product. Remembering that we are dealing with either calcite or dolomite in the ancient, whereas in the modern oceanic realm, we're typically dealing with aragonite and magnesium calcite that with time and burial will alter to the more stable form of low magnesium calcite. So in ancient rocks, we either see low magnesium calcite or dolomite as the dominant carbonate minerals. Each of those mineral phases has a differing solubility, and their relative solubility is going to be a function of several variables: crystal size, crystal heterogeneity, crystal defects, the internal porosity and permeability, organic matrices that are present, and the mineralogy being the most important. Calcite solubility, as this diagram shows, is a function of magnesium content. Because increasing amounts of magnesium inserted into the calcite lattice structure to form the crystal, it makes it progressively less stable. So if we look at modern carbonates, low magnesium calcite is quite stable. High magnesium calcite is the least stable, the highest solubility form. The proportion of magnesium carbonate in that lattice will control its solubility, with the much higher levels of magnesium carbonate, up around 15% mole magnesium carbonate, being the least soluble. Aragonite sits in there at around the same solubility as a 12 mol% magnesium carbonate calcite, high magnesium calcite. Remembering that we end up with these three forms of mineral when we go through the metastable stabilization processes in the subsurface. Aragonite and high magnesium calcite will alter to calcite. Aragonite typically does it by a process of dissolution and then reprecipitation. High magnesium calcite can go through that dissolution process to form a sparry calcite, or it may see a much finer replacement mimicry texture as it expels the magnesium carbonate, forming a much more detailed textural preservation. And we'll look at that in a little bit more detail in a few subsequent video chapters. The other thing to remember is that we are living in a time where aragonite and calcite are the stable mineralogies in marine waters. But there were times in the past where magnesium calcite and aragonite were not as stable, and low magnesium calcite was the stable precipitate from the world's oceans, for much of the Paleozoic, for example, where we had Paleozoic corals precipitating as calcitic form, not the aragonitic forms we see in corals today. You can see, based on these charts, that the relative levels of aragonite versus calcite, the grey versus the pink, varies across the Phanerozoic, reflecting changes in the magnesium-to-calcium ratio in the world's oceans. And that ties back to varying rates of seafloor spreading and to climate oscillations between icehouse and greenhouse, and also the associated eustatic styles and the extent of continental freeboard or carbonate shelf And we'll come back and we'll discuss these processes and controls a little later in the sequence stratigraphic module in this course. We also discuss it because it's important in terms of dolomite percents, and there's the Given and Wilkinson, one of the early curves, looking at dolomite stability in the upper right. But to come back to the mineralogy of the main contributors to marine carbonate sediments, some forms have had calcitic mineralogies throughout their evolution. So if we look at the planktonic coccoliths, which evolved in the mid-Mesozoic, or the pelagic foraminiferal association, the fusilinids, followed by the planktonic forams from the mid-Mesozoic onwards, they've always had calcitic mineralogies. Whereas the green alga, the bivalves, the gastropods, and the scleractinian corals, since the mid-Mesozoic onwards, have had aragonite as their dominant mineralogical form. The earlier forms of coral, not the scleractinians, but the tabulate and the rugose corals in the Paleozoic, had calcite, magnesium calcite, going to calcite, as the dominant form, as did the trilobites, as did the bryozoans, the crinoids, the echinoids, and the coralline and red algae. They've all had magnesium calcite skeletons, which tend to preserve as they alter to calcite, very fine, detailed texturing of the original biostructures in that shelly material. Brachiopods have always had a calcitic mineralogy across the Phanerozoic. Mineral phases here are related to changes in oceanic chemistry, and we'll come back to that discussion in a later module in the course. I'll mention dolomite here, but I'll look at dolomite in a lot more detail in that dolomite course. It's a topic unto itself. But if we take a plot of the proportion of dolomite, this is one of the original plots. This is Ronov's 1980 plot going from the Archean through the Proterozoic to the Phanerozoic. We can see that dolomites come into their own in the Proterozoic. They tend to dominate in the Phanerozoic, and this relates back to changes in oceanic fluid chemistry. The majority of those dolomites that we see are replacements. They also form cements in some dolomitized limestones. Various authors have noted that Precambrian dolomites have very well preserved original fabrics at the hand and microscopic level in most Precambrian dolomites, and have argued that primary dolomite mineralogies are a definite possibility in Precambrian dolomites, compared to most dolomites in the Phanerozoic having a secondary alteration origin. That's because there's a kinetic hindrance to dolomite precipitation. Likewise, with aragonite, low magnesium calcite and high magnesium calcite, these are the principal modern marine precipitates with little or no dolomite. And so factors affecting direct dolomite precipitation from seawater are influences like higher temperatures, higher partial pressures of carbon dioxide, higher magnesium to calcium ratios, lower sulfate and organic acid effects. The magnesium to calcium ratio was higher, CO2 levels were higher, and temperatures were higher, and sulfate levels were somewhat lower than they are in the Phanerozoic oceans, and so we tend to see dolomite dominating in the Proterozoic. What have we learned in our discussion to date? We've learned that modern marine carbonates are dominated by the metastable phases aragonite and magnesium calcite. Dolomite is a rare phase in modern sediments. Whereas if we look at ancient carbonate mineralogies, more than 90% of ancient carbonates is either limestone, as calcite, low magnesium calcite, or dolomite. And the proportions of calcite to dolomite vary regionally, across time, and with climate. Fluctuations in Phanerozoic ocean chemistry, specifically the magnesium to calcium ratio, influence the mineralogy of the dominant marine carbonates, both as shelly biomineralized accumulations and as inorganic precipitates. And lastly, the iron carbonate minerals, siderite, anchorite, ferro dolomite, are routine burial diagenetic cements in siliciclastic associations, more so than pure carbonate associations, because their iron is coming out of the clays. Carbonate mineralogy varies through time. Today, we have aragonite and magnesium calcite. In the past, we have low magnesium calcite and dolomite.